everyone, I'm Yuxiang Liu. I'm the postdoc in Professor ROSEI's group. I will introduce AFLOW-POCC. If you have any question, you can raise your hand, also for the audience online. You can click the link here for AFLOW-POCC. Before introducing the AFLOW-POCC part, we need to do some preparation works. First, we should disconnect and delay the runtimes first. Now we should download the binary of the AFLOW software. If you have done, we can set the environment and copy the AFLOW-RC files. Then let's install some software for figure plotting works, including the GNU plot, Magic, and text lab. This time will take around 1 minute. Have you finished the installation about this software? and we need to make some directories to save our files. Okay, as we know, the ideal crystal means, means the items are arranged perfectly ordered, and there will be some unicell or periodic patterns that can be repeated along all the directions and extended infinitely. At the same time, the chemical composition in the system is consistent and uniform. However, this is an ideal case. In reality, the crystal always contains various kind of defects, which will introduce disorder to the system. So here I want to divide the disorder into two categories. The first one is crystal disorder, and another one is chemical disorder. In the case of crystal disorder, the items are not arranged ordered anymore. It means there is no periodic pattern anymore. Maybe in some local place, for example, here we can find some short range order, but the system like long range order. As for the chemical disorder, there is a chemical composition variation in the system. For example, like this one, 25% of sulfur items are replaced by the selenium items. Today we will focus on chemical disorder. And if we want to theoretically calculate a chemical disorder system, first of all, we need to build a large enough supercell to accommodate the different chemical composition species. I would like to take this zinc sulfide selenide with 25% selenide and 75% sulfur items as an example. First of all, we need to build a large enough supercell to accommodate the selenium items and the sulfur items. The position of selenium is random because in nature, the sulfur and the selenium should be put randomly. So only if we have a large enough supercell, we can put them in the place with a randomness. At the same time, we couldn't only build one supercell. We need to build a series of configurations because only in such kind of case we can consider the statistic characteristic of chemical disorder system. However, this is a very challenging task for theoretical calculations because the computational cost is very expensive. So AFLOW-POCC aims to solve this challenge. Now I will introduce how does AFLOW-POCC to model the chemical disorder. In this system, we have a 0.25 selenium item and 0.75 sulfur items. Firstly, we need to determine the supercell size to accommodate our chemical compositions. The smallest supercell size should be 4 because only in the supercell with size of 4, we can have one selenium atom and 3 sulfur atoms. We couldn't build, for example, 3. The size shouldn't be 3 because the selenium or sulfur atoms are float. Because in nature, we don't have such kind of structures. So the smallest size is 4. Then we need to determine how to construct our supercell. To simplify the problems, I plot 2-dimensional figures here. This point can be considered as atomic position. So we need to construct a structure with size of 4. These 7 structures, the size are all equals to 4. So we can build 7 different types of shapes. Similar, let's go back to the 3-dimensional crystal structure. So we can also build 7 different types of supercells. Here we call them derivative superlattice. Now we have determined the shape of supercell. Then we need to consider the position of the one selenium atoms. Let me take this as an example. In this superlattice, we have 3 sulfur atoms and 1 selenium atom. The selenium can be located at this place, this place, this place, or this place. So we have a 4 method to decorate, to put our selenium items. We call it decoration permutations. So in this case, we have 3 types derivative superlattice, and for each superlattice, we have a 4 method to decorate our selenium atoms. Though we will have 28 configurations. Let's go to the practice directory, and then firstly, let's check the perfect structure of zinc sulfide. We should give the prototype of zinc sulfide, and the minus 1 to ask to change the lattice parameter direction. We can see here we have two species. First one is sulfur and the other is zinc. At the same time, both of sulfur and zinc, they only have 1 atoms in the system. Then let's switch to build our POCC structure. There are 2 methods to build POCC structures. We can build by positions or species. This is another postcard of another. It is a postcard for another prototype structures. Here we have we can see that we have 2 types of species, A and B. So A is labeled by species 0 and B is labeled by species 1. Different from the zinc sulfide, we have 5 items in the system. So we can these items can be labeled by position 0. This is position 1, and this is position 4. To the last one is position 11. So let's try to build POCC structures by position method. We can see here, this is the prototype of the zinc sulfide, and this is the the elements we want to build our structure, sulfur, selenium, zinc, and this is the POCC parameters. Because we can go back here. The first position is sulfur, but now but this position is partially occupied by sulfur and selenium. So here the 0.75 is sulfur, and the other 0.25 is selenium. So here is the parameters for first position 0. For the position 1 is totally occupied by zinc, so is 1 by C. We can run. We can see here is 0.75 sulfur and 0.25 selenium. Let's go to the second method to build POCC structure by the species. These are the same. Let's go to the POCC parameters in details. Because based on this, the first species, the species 0 is sulfur. So we can use S0 here, and 0.75 is sulfur, and the other is selenium. So the species 1 is fully the zinc. So this is the parameters for POCC. We can evaluate. We get the same results as the first method by the position. Oh, I want to compare the difference between the postcard and the part card. The part card is the crystal structure generated by POCC. We can see here for postcard, this number represents the number of atoms. In postcard, this must be integers. And this is the chemical formula, and this represents the species of the atom. But in part card, you can see here is the float number is partially occupied by different species. Here is an exercise to generate the POCC structures for carbides, and you can try to generate the structure by the different method, the position and species. We have 5 minutes to do this, and I will do this for you later. could firstly check the postcard of this parent structure. You can see here in the system we have a parent for the parent structure we have two species and there are 8 atoms totally in the system. So based on our question, the species B is partially occupied by 5 metal elements. And so if we want to build POCC structure by position method, the position 0 is fully occupied by carbon. So it's a 1 by A. But because from position 0 to position 3, they are all totally occupied by carbon atoms. So from position 0 to position 3, they are all separated by 1 by A. As for the position 4 to position 7, they are partially occupied by MO and B, TA, B, and W. So they are decorated by the point 2 by B, by C, by D, by E, and by F. So this is our result. Position A is fully occupied by carbon, and the other positions are partially occupied by the 5 metal elements. If we switch to species method, is relatively simple than the method by the position, because we only have 2 species, and species 0 is 1 by A, and by the species 1 is partially occupied by the others. Now we get the same result. Do you have any question about this?
Did you change the crystal structure from the suggested one?
Yes,
Because that's not a structure I'm getting.
This is the protocol for this, because here we have different numbers of, the atom number is different from the species. You can compare the differences between these 2 methods. Here you should use this is the protocol for this structure.
Sorry, so down the line, do you use that or do you use something different?
Oh, sorry. Oh, here I used. Oh, sorry, I made mistake here. Yeah, it should we can also do this. Actually, here this is another filter tab, and we should give the parameters for these filter tabs, and then the other operations are the same, and I will update these results later in this Jupyter notebook. Here I'm sorry to make these mistakes, and I will update these results later, and here I give the answer about another filter tab. Is this one. Then I will introduce how to calculate the optimal supercell size for the the supercell size to generate our POCC structures. This column represents the supercell size, and this number. The left one represents the total amount of items of sulfur, and this is represent the selenium, and the right part the total the total number for this species. We can see that if the supercell size is only 1. We will have one sulfur atom and 0 selenium. So the stoichiometric of sulfur atom is 1, but for selenium the stoichiometric is 0. So the arrow for sulfur or selenium are both of 0.25. If we increase the supercell size to 2, there will be 2 possible cases. The first one is we will have 2 sulfur atoms and 0 selenium atom. And another case is we will have 1 sulfur atom and 1 selenium atoms. For both of these 2 cases, the stoichiometric arrow equals to 0.25. So we need to increase our supercell. When we increase the supercell size equals to 4, we will have 3 sulfur atoms and 1 selenium atoms. So in such case, the stoichiometric equals to our given chemical formula. So we choose 4 as our optimal supercell size. And we can use this comment line, minus H and I, to calculate our optimal supercell size. Here we use the pipe signal and then use the common line, minus H and I. We can see here the superlative size is 4. Then we can As I mentioned a while ago, we have 3 different types of derivative superlatives and 4 different types of decoration permutations. Thus, we can get 28 configurations. However, in general, we won't calculate all these 28 configurations because there are some degenerate structures. What is degenerate structure? If the configuration structure they have the same energy, they think they are degenerate. We should exclude this degenerate structure to save the computational time. So we only pick the structures have different energy. We think they are unique. So after the energy calculations, we get these 7 unique supercells. So we only consider these 7 unique supercells. We can use this minus HNF cell comment line to calculate the unique configurations for our POCC structure. You can check, we get this, the postcard for this 7 unique supercells. When we determine the unique supercells, we should prepare our input files for further quantum mechanic calculations. And so we should go to our working directory and execute this command line to generate a flow-in file for the whole system. Then we should go to the directory which contains the AFLOW-in files and to execute a flow run to generate all the input files for each unique supercells. You can see here, this, or maybe also from here you can see. We have 7 directories for each unique configurations, and there will be a flow-in files for DFT calculations. If we finish the DFT calculations, we need to calculate our disordered system properties. Actually, AFLOW-POCC, it decompose the disordered system into a series of ordered systems, and we calculate the contribution of each ordered system to the disordered system. Then we can calculate the properties of disordered system and the contribution of the probability of each ordered system is based on the Boltzmann distribution. The HF means the formation energy of the system. GS represents the ground state. So we calculate the distance between the ordered system and the ground state. And KB represents the Boltzmann constant. T is the temperature, G is the degeneracy. So if we have this probability, we can calculate the disordered system properties. So let's summarize the procedure of how does POCC to calculate the disordered system. Firstly, we should determine the optimal supercell size to accommodate our partial occupations, and then we generate the unique supercells. These are actually these unique supercells are this ordered system. Then we calculate the DFT calculations for each ordered system. Then we get all of these structures properties, and based on the Boltzmann distribution, we can calculate each subsystem's contribution to the disordered system and get the properties of disordered structure. That, for example, we can calculate the density of states, the band gap, or the magnetic moment of the system. Because we couldn't execute fast calculations on corollary, so this is the pre-calculated results we can download and to see how to calculate the dose for the zinc sulfide and selenide. Let's go to the result directory and execute a flow run. It will calculate the dose for disordered system. If the calculations come down, we can execute minus plot dose. It will plot the dose at different temperature. We can see there are, this is the dose at different temperature from 0 to 2400 Kelvin. Here I present the petals of the structure at 0 Kelvin. For SPD orbitals, and you can see there are many energy states at around -6. So let's do an exercise to create the AFLOW-in file for carbides, and this is the prototype, and you can check what's the size of the optimal supercell and how many unique configurations for this POCC structure. So the optimal supercell size is 5. And then we can use minus HNF cell to get the unique configurations. Postcard for each configuration. And then we can go to the directory, contain the AFLOW-in files. Oh, this we can generate the AFLOW-in files for the system. And then go to this directory to generate the AFLOW-in files for each unit configurations. That is running, and I want to show for the first exercise, the prototype's parameters for this is this is the parameters for this prototype, and you can I think it's waiting master running. Oh, here you can see this is the current structure for this prototype, and you can partially change the species A and species B, and I will update this answer for this prototype later. Oh, you can see here we generate should be there should be 49. Oh, sorry. Yeah, should be 49 unique configurations for this structure. There is another exercise due to the time limitation. You can do this by yourself later, and I will update the answer to our workshop website, and you can go there to make sure if you do right or not, and take it as a reference. And for more details, you can visit AFLOW school website and to see the video. And if you have any other questions you want to ask me, I will be there for in next 2 days. You can ask me. Thank you.